Hello, my name is Luca Callegaro, and my talk deals with an Ampere project, Graphene Impedance Quantum Standard. You can see the list of authors, which are also the project partners. The project, Graphene Impedance Quantum Standard, is a joint research project of the European Metrology Programme for Innovation and Research, Ampere. The Ampere program is coordinated by the European Association of National Metrology Institutes, Euramet. The project duration is of 3 years. It started in July 2019 and it will last until June 2022. Among the goals of the project, there is the realization of the impedance units in the revised SI, so traceable to fundamental constants. The shortening of the primary traceability chain of calibration for impedance at stakeholder sites. The strengthening of the calibration facilities of smaller RMIs, calibration centers, and industry. The development of quantum electrical standards for all metrology institutes, the fabrication of robust graphene-based quantum standards, the development of cryocooler systems for all-in-one operation of these quantum standards, and an effective knowledge transfer. The project partners are listed on the right. You can see the logos. And they are mostly distributed in Europe. PTB is the project coordinator, and we have two important partners in Asia. Among the partners, there are national metrology institutes, an university, and a research center. The project implementation is distributed in 4 work packages. Work Package 1 deals with the graphene devices for AC quantum Hall applications. Work Package 2 with digital and Josephson impedance bridges for the realization of capacitance. Work Package 3 aims to connect Work Package 1 and Work Package 2, realizing graphene AC quantum Hall resistance systems with digital and Josephson impedance bridges. And Work Package 4 deals with creating impact. I will give you now an overview of the project progresses in the various work packages. First of all, you can see here images about graphene devices. The focus is on graphene on silicon carbide, which is grown in a furnace at high temperature in the inert atmosphere using a so-called susceptor in graphite that you can see in the middle. On the top right, you can see the complete devices connected to its package. Both individual devices have been realized. On the bottom left you can see several devices on the same chip, but also arrays, and in the bottom you can see the design of a 10 array of 10 devices put in series with triple series connections. For what concerns bridges, the research focuses on 2 kinds of bridges. Josephson impedance bridges, where the waveforms are generated by Josephson synthesizers, and electronic bridges, where instead conventional electronic is being used. Here you can see the development of a Josephson bridge at PTB. On the bottom you see the Josephson pulse-driven sine wave generator. The present 2-terminal pair Josephson quadrature bridge that can measure a capacitor in terms of the quantum Hall resistance is being extended to 4-terminal pair. You can see the picture on the top right. For what concerns electronic impedance bridges, you can realize both ratio bridges to compare the AC quantum Hall resistance with a resistance standard. And here you can see a realization. The original bridge has been optimized to perform measurements on AC quantum Hall effect. And I will show you later that this bridge has been also used to perform the first successful AC measurements on graphene-based devices with a digital bridge. To realize capacitance in terms of resistance, you need a quadrature bridge, and this is an electronic impedance quadrature bridge being developed. At the present stage, the bridge, which is a 4-terminal pair, can reach a transfer uncertainty of 2 parts in 10 to the 7. It's particularly simple in its network. And at the moment, it compares resistance and capacitance standards. Of course, the aim is to go to the quantum Hall effect in graphene. To perform these quantum Hall measurements, it is necessary to develop dedicated cryogenic environments which can be suitable for AC quantum Hall effect measurements. You need shielding and coaxial cables in order to minimize the effect of stray parameters. On the left you see a shielded sample holder. The design is being now refined. In the middle you can see the realization of a coaxial probe which is devoted to perform measurements on small size cryomagnet up to 6 Teslas. On the right you see a cryocooler environment that can host with a proper magnetic shielding both Josephson and quantum Hall devices in the same cryostat. So it's able to host the Josephson bridge and the quantum Hall standards at the same time. Here you can see first DC measurements performed on the new graphene devices. On the left, in blue, you have the quantum Hall effect resistance versus the applied magnetic field, and in the same graph you see also the longitudinal resistance in red. On the right, these same curves have been measured by precision measurements, and you can see that the quantization at part per billion level is there even at magnetic fields as low as 4 Teslas. These are measurements on graphene devices developed at GIQS. On the left, top left, you can see a transportation device that has been used to transfer the device from Korea to the Czech Republic and vice versa. In the graph, you see the results of measurements performed in Korea before and after the transfer to the Czech Republic, and in the red dot is the measurements performed at CMI. So we have a compatibility of part per billion level, and the device survives the transportation and the storage. In the bottom curve, in violet, you see the measurements with the AC electronic bridge, and the curve is shows a deviation versus the DC measurements of part in 10 to the 7, and the shape of this curve is different from the one you can expect from a gallium arsenide device. You can follow the project both on its web page, or on a dedicated LinkedIn group. If you are interested in the development of the project, you can consider to become a stakeholder, so just contact me for that. Thank you very much.